Okay, the other major topic of this section is to look at creating the equation of a plane. You'll be really tempted to try to memorize the equation of a plane, and that is really a bad idea. Instead, draw a picture. So there's x naught, y naught, z naught, or x0, y0, z0 representing a specific point on the plane, and x, y, z without the subscripts representing a generic point on the plane. You'll see that I've got two such points drawn in this picture. And the point is, all of the things that we've already said regarding dot product and cross product and so on will be very helpful for us here. So what you see in blue, for instance, if you do x minus that specific number x0, again, whatever number it is, and then y minus specific number y0, depends on the problem, z minus z0, that in angle brackets, that represents a generic vector. So what's shown in blue here, what's shown in blue there, those are two examples of the generic vector. And each generic vector, as we see here and here, happens to be perpendicular to the normal vector that jumps out of the plane. And because of that, if you take your normal vector and you dot it with the generic vector, you should get the zero scalar. And then you can replace that normal vector, as is often written, let's just say with ABC in angle brackets, and then perform that dot product. So we'll use our parentheses here, but dot product is as you expect. Multiply first components, multiply second components, multiply third components. And there's still this equals zero. Remember that zero coming from, that's what happens for perpendicular vectors. The dot product results in the zero scalar. So don't try to memorize this here. I've had people who should have the A, B, C out here, instead have them after the minus signs in the parentheses, and the things that were after the minus signs in the parentheses were out in front. I mean, all kinds of things go wrong. There's no point memorizing this. It's so much better to really reinforce the concepts that have been already looked at earlier instead. So often understanding takes less effort than memorization. What's really going on here, right? So just to spell out the details, is the vector from this point to one of these generic points is this. That vector lives in the plane, and so it has to be perpendicular to n. And so because the blue vector, or one of the blue vectors, has to be perpendicular to the normal vector, when you dot product, you get zero. So I don't even want to call these four steps, right? I want you to just think about what's going on and apply a process. So in step one, you practice, for instance, getting a vector that is created from one point to another point. And in step four, you practice the orthogonal vectors theorem. So that's just much better. So let's go through the process. I'd like to write a scalar equation for the plane with normal vector 2, 3, 4, which goes to the point 7, 6, 5. It looks something like this, right? So here's that fixed point, and this point here, I know it's drawn here, but that's the necessary evil of drawing. This point could have been drawn over here or there, or it's just somewhere inside the plane. And so we have this blue vector, and it needs to be perpendicular to this vector here, right? So let's just form what that blue vector looks like, right? Shouldn't it be, this is a point, this is a point, so you do the coordinate of the final point minus the initial point, so you get this vector right here. And now we just need to dot that vector with the 2, 3, 4 vector, and we're going to declare that needs to be 0 to create this 90-degree angle. And if we just write out what the dot product does, we'll have 2 times quantity x minus 7 plus 3 times quantity y minus 6 plus 4 times quantity z minus 6 equals 0. And that's really it. I mean, that's a scalar equation. We could simplify by distributing and, collecting the constants together. If we want it to look kind of nicer, we could add 52 to both sides. This is sort of typically considered simplified, but in some sense, getting to this step, that's really the goal right there. So please don't memorize. Again, looking back to the first scalar equation that I'll highlight up here, right? It should be 2 times quantity x minus 7. People try to memorize things and do 7 times quantity x minus 2. And this is not a story about try to memorize it better. That is not the story here, right? The story here is to say, instead of trying to memorize some procedure, there are things that we've seen that are helpful to look at. And so relate what's going on with the equation of a plane to concepts we have looked at. It's a good chance to practice some concepts we have seen. So here's a follow-up. We just got the equation 2x plus 3y plus 4z equals 52. Now, the thing is, we could actually use this equation to find another point on the plane. The only point we happen to know of on the plane right now is 7, 6, 5. So let's find a different point on the plane. to do that, I'm just going to pick one of the variables to be 0. I just happen to pick x to be 0. I could have picked x to be 7. I could have picked, oh, no, maybe, okay, I shouldn't pick x to be 7. I could have picked x to be 25, but I picked x to be 0. You could pick something else if you want. I'm also going to pick y to be 0, just out of a matter of convenience or laziness, but you could pick y to be 300 if you really wanted. And then let me just plug in, and I'll have 4z equals 52, so z equals 13. Therefore, 0, 0, 13 is a point on this plane. As a second answer, just to try different things, instead of picking x and y both to be 0, I'll pick two other variables. How about y and z to be 10 and 3 respectively? I'll plug those in, and I'll have 2x plus 30 plus 12 equals 52, and I solve and I'll get x is equal to 5, therefore 5, and then the comma, the numbers 10 and 3 that were picked, that order triple forms another point on this plane. Okay, you may also notice, I should just point out that the equation that we had at the top, you look at the coefficients 2, 3, and 4 in front of x, y, and z, and you can still sort of read that information about the normal vector inside this scalar equation. Okay, so to really practice what I mean by that, let's look at this. 4x minus 5y plus 17z equals 3. That describes a plane. What is a normal vector for this plane? Well, just read off the coefficients of x, y, z. So 4, negative 5, 17 is a normal vector for this plane. How about 3x minus 5z equals 11? What's a normal vector? 3, 0, negative 5, right? The coefficient of y is 0 this time. By the way, for normal vector, there isn't just one, so I don't want to say the normal vector. Any non-zero scalar multiple of 3, 0, negative 5 would also be a normal vector for this plane. So, for example, if I scalar multiply by 2, I'll have 6, 0, negative 10. If I scalar multiply by negative root 7, then and I wrote it in the other form instead of an angle bracket form. Here are two other, the point is right here, and then after the word and, these are also normal vectors for this plane. So just pause and think about this for a moment. Does this make sense to you that any non-zero scalar multiple of a normal vector is also a normal vector to the plane? I mean, does that make intuitive sense from a geometric perspective?